Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and we are at the topic of recurrent neural networks, which is topic number 8 in the list of topics covered in this course. And the subtopic is B, so it means that the difficulty level is from easy to moderate. And this video is prepared using the supplemental website www.easymcq.com/GoGet, which is a personalized learning management system. Now, this is the way the content is delivered in this course. So this is not only the future of content delivery, it is also the present of content delivery, because there are literally 100 million users which are using this approach for online content delivery, for learning, and for getting to know different topics and subjects. And the benefits of this approach is listed in front of you. So the green color link, hyperlink, is the address of the personalized learning management system, and which is developed using the content delivery approach. And the key 6 features are available in the form of 6 videos, which I strongly urge you to view. And the address of these videos is given in blue color. And the beauty of this approach is that it provides basic and advanced text search in the contents of the material. It also supports people who have visual disabilities by setting the font, color, spacing, etc. of the content to view. And it is also optimized for the small screen of smart handheld devices, and you can track your progress also, what you have covered, what you need to cover, and you can also test yourself about the knowledge accumulation, the knowledge assimilation, and identification of weaknesses. So there are two approaches of knowledge transfer. One is the question and answer based approach, the other one is the traditional slide based approach. So in this video we have adopted both the approaches, and the Q&A approach is proactive, it is adaptable, and it is engaging, and it is also provoking thought, which machines have difficulty in doing. And it also contains the details which are of the traditional approach. So this is a blended approach. This is the best of both techniques. So this is the list of topics which are covered in this course, and we are currently at topic number 8, which is recurrent neural networks. And these are the details of that topic, and these details are in the form of questions and answers, which are concepts. So the easy ones are in yellow color, then the easy to moderate in in green color, then the blue color, and so on. So without further ado, we move on to the details of this lecture. So we are at lecture 8B of deep reinforcement learning, recurrent neural networks. So the concept which we are looking at right now is how gradient descent optimization is implemented as back propagation in recurrent neural networks. So the content which we will be covering is listed in front of you. So which consists of the following bullets, you can see them, and there's a wonderful diagram also which explains the concept. We looked at it before also, and if I click on more, so these are the details for those bullets, and then there are less details. So let me first go over some background and then I will explain. So implementing gradient descent via back propagation, which will be through time, because we are looking at recurrent neural networks. So what it does, it allows deep reinforcement learning agents, like the agent which is in control of autonomous vehicle, to learn the temporal relationships, the relationships in time, and the relationships along with the dependencies across a sequence of observations across time. So what forward pass does, that it processes the inputs sequentially and builds the hidden state memory. So we are looking at non-Markovian system. And the compute loss aggregates the errors. The error which was versus, basically we are talking about the training phase, aggregates the errors across all time steps, right? Across all time steps into a scalar objective, not a vector. So what happens is that the back propagate through time extends the standard back prop, which we have covered in neural nets, across the temporal layers. And how it is done? By unrolling the network and accumulating the gradients at each point in time. So what we do is we do gradient clipping and regularization right? And that kind of guards against the instability. And what contributes to the instability is the vanishing or exploding gradients. Okay? And a learning rule to adjust the parameters. So all of these steps are taken together that allows the RNN based agents to learn policies and policies in the context of reinforcement learning that I will cover, and the value functions that they rely on, not just on instantaneous observation but on sequences in time. What it does that it improves the performance in partially observable or temporarily complex environments. Again, reinforcement learning. So what an RNN does, it can be thought of as a sequence of neural networks, the current sequence of neural networks that are trained sequentially, one after the other, using the back propagation. Now, in a fully recurrent neural network, the outputs of all neurons, they are connected to the inputs of all the neurons. We are like an unfolding. So now, so for FRNN, okay, the most generalized RNN and various types of RNN can be derived by how? By setting some of the connection weights to 0 to indicate the lack of connection between the corresponding neurons. So let's look at this diagram on your screen. So what this diagram shows is the implementation of back propagation. So the left cell over here, this one, is the basic input, hidden and output weights. All right. What are those weights? Those weights are U, V, and W. U, V, and W. All right. On the right is the unfolded to show the same progression but at a certain time, right? And at that time, the weight, okay, and the time corresponding times that occur using back propagation in gradient descent. So the details are given here, all the details. So I would suggest that you read the details. Now let's go over these bullets. So in forward pass, the recurrent in forward pass, the recurrent neural network processes inputs in a chronological order, in with reference to time. What they do is updating its hidden state at each time step, because we observe the consequence of the hidden state. So this hidden state encapsulates the past information, okay, uh, enabling the network to base decisions not only on what is happening right now or what is happening currently, but also using the historical data, using the earlier context. So what happens is that the outputs for each time step are generated, ensuring that the temporal dependencies are preserved. Temporal dependencies, say for example, because certain sequence of words, say in language recognition, that has to be there, otherwise you will lose the meaning. So then compute the loss. Now after predictions are done at every step, prediction means that what is going to happen, losses are calculated, right? Because prediction, you remember I gave you the example of the blind man with a stick descending a valley. So makes a prediction that what's going to happen, and of course it's a prediction. So the difference between the actual and the prediction is the loss. So losses are calculated by comparing outputs to the target values. Now these so we are looking at errors per step. So all these errors are summed up, or you can average them also across the sequence which was followed, and a single scalar loss is computed. A single value is computed, okay, over here, that captures the performance over time. Now this unified loss is used to drive the parameters and to optimize the parameters, which is the biggest advantage of deep learning. So that is not human parameter driven. Now back propagate through time is not the standard back propagation, but it's the extension of that back propagation. and it is over the temporal dimensions with reference to time. And how it is done? By unrolling the recurrent neural net over time, which I've shown you, which is here also, and propagating the error gradients backward across each time slice at time t, at time t minus 1, at time t minus 2, and so on. Now, what happens is that the gradients get accumulated, okay, across the shared weights, because if you recall, the weights were not changing. So, what it does is enabling learning of the temporal dependencies, that at what point of time the relationship between this at time t and at time t plus 1 or time t minus 1. However, the issue with this approach is that it can result, or it is affected by, vanishing or exploding gradients. And whenever we have vanishing or exploding gradients, the the system loses the stabilization that we have covered. So again, I would strongly suggest that you keep on revising the prior material so that the next material is easily comprehensible. Now, gradient clipping and regularization. Now long sequences can result in instability because things can change. So what we do is we perform the gradient clipping, and that gradient clipping constrains the magnitude of the gradient. So when that clipping is done, then of course that prevents exploding updates of the gradient. So as to maintain stability. Now then other things are used, such as regularization techniques like weight decay, which also prevent large weights. And of course it improves generalization, because the large weights can result is memorization. So truncated so truncated basic truncated back propagate through time, okay, limits back propagation to a window fixed window in time. So what happens is that we establish a balance between stability and the temporal learning. And of course there's no set formula, right? So now update the weights with gradients obtained. Weight matrices like for recurrent or input and output, they are updated using the gradient descent or advanced optimizers like Adam. Adam we also covered. So the learning rate scaling and optimizer mechanics ensure stable learning. So we achieve stability. And the hidden state management like reset or carry between sequences, right? That helps control the temporal continuity during the training. So we have to strike a balance. So here are the details. I would suggest you go over these details, and here are the references also. So we move to the next Q&A, or the next concept. And the next concept is, what are the different recurrent neural network input output architectures? Okay, and draw them also, and give the use case applications also. So these are the standard. There is a fifth one also, but I'm not covering it. So these are the four standard ones, and we have these. This is how they look diagrammatically, right? I will discuss them with you also, right? So this is the most straightforward one to one, and there are two types of many to many. There are two types of many to many. Anyway, okay. So what are these architectures basically, and what do they mean? So the input of the RNN and the output architectures define how the sequences of inputs are mapped to the sequences of outputs. How the sequences of inputs are mapped to the output. How the sequences of input are mapped to the output. Okay? Because it influences both the model design and the optimization strategies. So the basic types are 5. I'm covering 4. So there are too many to many. One is the one which we covered here, many to many synchronized, and then there is the many to many encoder decoder. Now each of them supports different temporal scenarios. For example, from no history context to full sequence translation. No history to full sequence translation. So in deep reinforcement learning, the choice of the right architecture is crucial. For example, many to one for summarizing the trajectories, many to one, many to many for time step actions, or encoder decoder for forecasting. Now there are different optimizing techniques like loss placement, gradient flow, gating, and so on. So they are adapted accordingly. And what they do that they ensure stable learning over time. In the previous Q&A, we discussed how to ensure stability and proper alignment of inputs, outputs, and temporal dependencies. So we have to be careful about which one to use and where. So if you look at one to one, all right, if we look at one to one, so there is a single input, then that maps to a single output. It's very simple, straightforward. It doesn't leverage temporal context and just behaves like a standard feed forward network. And of course, that is not a true sense RNN, so it is rarely used in sequence tasks. But of course, it is useful for baseline or when no sequence dependency is needed. So this is just for the sake of the definition that we have a one to one. So now let's look at one to many. Now from one input, the RNN produces a sequence of outputs. From one input, this is the input X here, one input, and produces multiple outputs, right? Or multiple and a sequence of outputs. Now it's used when a seed or input, this is the seed input, expands into a sequence like captioning. This is expands into a sequence. Now this model must maintain hidden state and decide when to stop the output. Otherwise, it can go on indefinitely. Then is the many to one. Many to one, the RNN reads a sequence of inputs. Many to one, sequence of inputs. This is the sequence of inputs. Okay. I'm sorry, many to one, sequence of inputs, and there's only one output. Reads sequence of inputs and outputs a single value or the label, right over here. Now, it kind of summarizes the temporal information into one decision or classification. So obviously it's used for prediction or summarizing or decision making tasks. So which model to use depends upon the application. Then is many to many synchronized. Now input and output have the same length. So we have, say for example, these are the inputs and these are the same length, and producing one output per time step, one output per timestamp, and so on. And it is useful in tasks like tagging or frame by frame classification, okay, where each input needs a corresponding output. Now then is the last one is the fifth one, which is the many to many encoder decoder. The input sequence length differs from the output length. Just hold on for a second. So this is many to many encoder decoder. The input sequence length differs from the output length. So input is the input sequence, this is the output, and they can differ in length, and uses separate encoder and decoder RNNs. And it is used in translation, prediction, and generative tasks. Why? Because for those tasks the alignment is complex. That's the reason. So the details are here. This is the background, and these are the details. I would suggest you read the details, and there are the necessary references also. Okay, so now we move on to the next concept or Q&A, and that is how to unfold recurrent neural networks, and of course show a diagram also. So unfolding, this is what we are interested in. So at time step 1 we have h1, so we have x1 h0, and so different time step we have different values. All right, and here I will explain all of this. So these are the topics or subtopics we'll be covering. Okay, and so what we are looking at is, so unfolding an RNN transforms its temporal recurrence into a deep feed forward like chain across time, which we have discussed not in detail but briefly. So what it helps that it enables the standard gradient based optimization. We kind of unfold it. Now, when we visualize the unfold or unrolled architecture, it clarifies how the hidden states and the inputs propagate through time. Okay, and how weight sharing works. Because remember that this is not fully connected, right? So there's sharing. So gradient computation across back. So that gradient computation across time sums the contributions from each time slice to update the shared parameters. Okay. But what happens that over many time steps, it can happen that if you look at that loss volume or loss surface, the gradients may vanish or they may explode, which affects and which kind of hampers the learning. So to manage this, gradient clipping is used, truncation, back propagation, and gating is done like in LSTM and GRU architectures, which we will cover briefly. So in deep reinforcement learning, unfolding and these stability techniques, what they do that they allow the agents to learn from sequences of observation and actions, and then adjust the parameters based on extended temporal dependencies effectively and hopefully reliably. Now let's look at these bullets one by one. So more detail is here. So with reference to the concept of unfolding, that we have discussed a number of times. So visualizing the unfolded RNN. So we have the original RNN and we have the unfolded RNN. Okay. So each time step is drawn as a layer with hidden state connecting and linking successive slices in time. And of course, that weight sharing is also annotated. Now, this diagrammatic view helps in understanding how information and gradients kind of move through the time while the training is done. Okay, that is shown here. That is figure 1. That is figure 1. This is what is meant by figure 1. This figure 1 is this. Okay. Then is computing the gradients. Computing the gradients. Now, after unfolding, gradient computation uses chain rule across both layers and time. And each parameter and the gradient of each parameter is the accumulated sum across all time slices where it's applicable. So what it does that it enables learning from how past inputs influence the future losses. So that is figure 2. This is figure 2, computing the gradient. And then we have handling vanishing and exploding gradients. Handling vanishing and exploding, which is figure I'm sorry, this is not figure C, it is figure 3. So unrolling many steps risks gradients decaying or growing uncontrollably in the past. So we use the techniques like gradient clipping and truncated backpropagation and gating architectures. Why? To manage the loss of signal or instability and ensuring robustness in training. So that is shown here in figure 3. This is a typo, so this is figure 3. Right? So I can zoom this also for you. So now what we can conclude from here that training is very complex. Training is very complex and it requires a lot of challenges.